Let us now study about diffraction at a single slit. Single slit basically means that there is a small gap between two opaque materials. As seen here, we have two opaque materials between which there is a gap. This gap acts like a slit. Here it's been ideally magnified, but the gap is very small. Generally, the gap is of the order of millimeter or micrometer. So what happens is, when light falls on this gap, we can assume that each point of this gap acts like a wavefront and produces secondary wavelets. These secondary wavelets would superimpose on the screen. So each of this, from Huygens principle, we know that each point acts like a secondary source and produces secondary wavelets. These wavelets would superimpose. So in case of diffraction, it is superimposition of different wavelets from the same source. On the screen, we get alternate bright and then dark region. This region here is called as central maximum, and this region here is called as first minimum. This is called as first secondary maximum. This is called as second minimum. This is called as secondary maximum. That is these are called as secondary maximum. These regions are called as secondary maximum. This is called as first secondary maximum. This is called as second secondary maximum. This is called as third secondary maximum. We have a central maximum, secondary. The reason that you want to differentiate between these two, because unlike interference where every bright band at same intensity, same width, here the intensity as well as the width also varies. Hence, to differentiate this, we call this as primary maximum, this is secondary. To arrive at condition where a given point, for example this point, if we want to find out whether we get a dark band or a bright band, and let the distance between these two be some d, then if we look at the point P here, let the angle made by center line with this be called as theta. So we can find out at what angular separations we get bright or dark bands. To solve this, we can assume that the slit opening we called as D to be divided into n parts. We can divide this into n parts. Since the distance between the two slits is d, the distance between this and this would be d by n. Assume that each of this part produce secondary wavelets and these would superimpose. So the net displacement at any given point we call as y. That will be because of displacement produced by n parts. And if we solve the equation, is not of this level, the substitution and solving of this is beyond this course. When we solve these equations, what we get is, we get a condition where the intensity at any point is given as psi naught into sine square alpha square. Alpha is equal to pi lambda into t. As told earlier, there is no need to understand how to get this. Then keep in mind that the intensity is not constant for all the bright bands, varies by this form. The alpha is given by this. And also, you want to find what is the relationship between path difference, the angle made. Then for nth minimum, the path difference is d sine theta n is equal to n into lambda as given here, where n is equal to 1, 2, 3, n is equal to 1, 2, 3. This is for nth minimum or the dark bands. For secondary maxima, the condition is d sine theta 2n plus 1 to lambda by 2. This is the condition for secondary maximum. Again, as discussed earlier, these are not true. Unlike the case of interference, we prove the condition for maxima and minima. Here, not proving it because the proof is beyond the scope of this syllabus. Just learn this formula to be true. You can verify this in other way around also, which we'll do in a minute. Understand that we'll treat all conditions. We have a slit like this. Been drawn very big here. This is this. We'll look at a condition for dark band where condition was d sine theta is equal to lambda, where n is equal to etc. Just call the points point R S. So center here to the screen. Since the distance between the center of this slit, call some point A, T, and one edge is d by 2. That is because distance between R and S is t. So this would be d by 2 and d by. It will be d by 2 and then d by 2 from here. Now what you can do here is, if you look at a given point here, and if this point is first dark band, then the condition is d into sine theta 1 is just lambda. So we need to find out why do you get dark band here. Understand this, it would mean that the wavelets going from here to here, the wavelets will have path difference of lambda, but you can divide this into two parts such that distance between point T to point S and point T to point R would be this path difference between point R to point T would be lambda by 2. Path difference between path T x delta of point R and point T would be lambda by 2. Path difference between point T and point S would be lambda by. Now we can assume that there are a lot of wavefronts here, also a lot of wavefronts here. So we'll take one wavefront here called as 1, and we call as dash. Similarly, let us take a wavefront called as 2 and a wavefront called as 2 dash. So we consider one wavefront or a point immediately below point R. There will be a corresponding point immediately below T, such that the path difference between point 1 dash would be by 2. Similarly, the path difference between point 2 dash would be lambda by 2. That is, for every corresponding point in the first half or the upper half of the slit, there is corresponding point in the second half, such that the path difference between those two points would be lambda by 2. Basically here, these two wavefronts are superimposing or interfering, and we learned to interfere in that whenever the path difference is a multiple of lambda by 2, it will be destructive interference. It will be destructive interference, which means we can say the wavefront cos of 1 and 1 dash would cancel each other because it will be destructive interference. Keep in mind that interference is a common term. where waves are superimposing. And for that case, we know that whenever in two waves superimpose and if their path difference is lambda by 2, that would give us destructive interference. Same here, every corresponding point in the upper half, there will be a corresponding point in the lower half such that these 2 points would interfere destructively. Means every point here would be negated or would form destructive interference with points below this, such that at a point say P will be a dark band. Keep in mind that here we're trying to justify to why do we get d sine theta 1 is equal to lambda for the first case. It would have been more easy to understand the same thing by deriving the formula, but then as I told earlier, derivation is not required in this course. Similarly, for second dark band, the condition would be d into sin theta 2 is equal to 2 lambda, because n becomes 2 in this case. And to understand this, we can divide the same region into now 4 parts. Because we had a point as earlier, use same symbol, it's called as R. So this point is called as R, and at a given point here, some point somewhere here, called as P2. At point P2, wavefronts from here would superimpose to form dark band. We're trying to justify the condition as to why it is dark band. This point would be a dark band form. Again, to understand this, it's a dark band here. We can divide the region into 4 parts now. We'll call this as, say, some R1, this point is R2, this R3. So the path difference between point R and S is 2 lambda. Means if we divide into 4 parts, the path difference between point R1 would be lambda by 2. So between any two consecutive points, similarly, the path difference between point R1, R2 would be lambda by 2. So between any two consecutive points, the path difference is lambda by 2. So we can use the same argument as used earlier also, that is, every point below R, there would be a corresponding point below R1 such that these two would superimpose destructively. Similarly, every point below R2, there would be a corresponding point below R3 such that even these two would have a path difference of lambda by 2, and even these two would interfere destructively such that at the point P2 we get dark band. We can use same argument for other things also, that is, if you want to find for third dark band, then the condition there is d sine theta 3 would be 3 lambda. In such case, we can divide the region into 6 divisions such that we call this as point R and point S. We can divide into 6 divisions, like 1, 2, 3, 4, 5, 6 divisions, such that the path difference between any two would be lambda by 2. Every point below R, there would be a point below R1 such that the wavefronts from here would interfere destructively, will cancel each other. The same argument what we used earlier, we can justify that even for this condition we get a dark band. This is the condition for dark band. Now let us look at the condition for bright band, where the formula was d sine theta n is equal to, use same thing given here, where d sine theta n is equal to 2n plus 1 by 2, where n starts from 1, 2, etc. Question is, why not to take n as 0, or why not take as minus 1 here? Because the central one is called as primary maximum and others are called as secondary maximum. The reason that we take n as 1. Put n as 1, we get the first secondary maximum. Now if we put n is equal to 1, and what we get is the first, we get the first secondary maximum, for which the condition is d sin theta 1 is equal to d lambda by 2. So here we can use the same argument what we used earlier to justify that this indeed would give us a bright band. Understand this. We look at the screen is somewhere here, and then a narrow slit. The slit has been highly enlarged here to get a view of the physical process. Call this as point R, point S. Here also we can divide into a number of blocks, but here we divide into 3 blocks. Let's call this as point R1, this is point R2. Again, the phase difference between any 2 points in each block would be lambda by 2. That is, if we have a point below R, there will be a corresponding point below R1 such that wavefronts or waves from here would superimpose destructively, which means every point below R, there is a corresponding point below R1 such that these two would superimpose destructively, but there is nothing to destroy or superimpose destructively for wavefronts from here. So this odd wavefront, that is wavefronts from here, would superimpose to produce a bright region. That's the reason that at this point we get a bright region. So just extending the argument used earlier, case of the previous case, what we did is when the path difference was lambda by 2 or lambda, the path difference, this is for dark band, it was 2 lambda or 3 lambda. In case of lambda, we divide it into 2 parts, where path difference between these two would be lambda by 2. These two was lambda by 2, such that for every points in this block, there is a corresponding point below to superimpose. So this would give us a 0 intensity. If the path difference was 2 lambda, then we divide that into 4 regions, like this. So the path difference between these two was lambda by 2, this was lambda by 2, again this was lambda by 2, this was lambda by 2. So we saw that for every point below this point, call this R, R1, R2, and then this is called as S. For any point below R, there is a corresponding point below R1 such that these two would superimpose destructively. These two would cancel each other. Similarly, these two would cancel each other. So whenever we have a multiple of lambda, we can divide into even number of blocks. Here it was divided 2 blocks, here 4 blocks, 6 blocks, and then here it was 8 blocks, etc. Whenever we have even number of blocks, for every block there will be a corresponding block which will cancel each other. So you can justify saying that for these conditions we get a dark band. But if it is an odd number, like seen here, like 3 lambda by 2, 5 lambda by 2, etc., here we divide into 3 blocks, like this. We call this as point R, point S, point R1, point R2. So the even blocks or the even number of blocks would cancel each other. So this is not cancelled. This wavefronts from here will give us light. Here also we divide into 5 blocks such that the 4 blocks as seen here will cancel each other and there will be 1 box remaining. So whenever the path difference is a multiple of the odd multiple, in that case we can say an odd number of block would remain uncancelled. That is what would give rise to the light or brightness. We can say that d sin theta n is equal to 2n plus 1 lambda by 2 is indeed the condition for destructive appearance, which means in this case we get bright. Again here, we're not proving it, we're trying to justify why this is condition for bright bands or dark bands using our intuition to